Okay, so the test is on Friday. It will cover from, well, basically SN1, SN2, E1, E2. Alcohols, SN1, eliminations of alcohols like dehydrations, up through, well, this time it'll also include the reactions. If I give you two reactions, which one goes faster, slower, they have the same rate, and then also electrophilic additions. So HBr, HCl, H plus H2O, all those. It'll be mostly mechanisms and writing products and determining the major products. And then there will be some of those faster, slower, same type problems. So Wednesday we'll have class, or I'll answer questions, so if you've got them, you should ask them soon, but otherwise we'll use Wednesday for that as well. I think the website is up to date. I think it was missing page 3 on the take-home quiz that I put up, but hopefully everybody got the take-home quiz that was in class, as opposed, because I think there were a couple pages, or there was a page missing.
Just to clarify, so we're not going to see this stuff on it, on the exam?
What stuff?
Like this is from the lecture that we did with corporate.
Oh, absolutely.
We will see it on the exam?
Yeah.
Okay.
Yeah. Yeah, why not?
Why not? You're right.
I'll decide about today's exact stuff at the end. So, okay. Okay, your take-home quizzes from the other day will be outside my door tomorrow morning for you to pick up. The answer key is already online. Okay, so in terms of where we're picking up from last Tuesday, we talked about all sorts of additions, BR2 in water, H plus H2O, HCl, etc. We ended up with these 3 reactions, just showing the idea that we can add H and OH a number of different ways depending on the reagent that we use. We could add H and OH Markovnikov, where the H and the OH would add 50-50 of cis and trans if we use H plus H2O. Which is this one. If we wanted to add H and OH anti-Markovnikov, we have to use hydroboration oxidation, which only adds cis. And then if we wanted to add Markovnikov but add the H and the OH 100% trans, we could use the mercuration demercuration. So those 3, yes, will be for Friday. The next reactions we want to talk about are, there's a triangular intermediate. It's an intermediate compound that's used that will actually end up with an OH attached to one carbon and a nucleophile added to the other, and these are called epoxides. So we just got to this last Tuesday. But epoxides have an oxygen attached to the two carbons. It's a 3-membered ring. IUPAC name is an Oxirane. And these are intermediate compounds. So in other words, I can make an epoxide, I can put it in a bottle, I can store it. It is a compound that's stable. It's not an intermediate, but because it has a triangular shape, things will add to it trans, to the oxygen, like all triangular intermediates. So the first thing is, how do we make them? How do we make epoxides? Well, there's a couple of step method, there's a one-step method. The first is from bromohydrins. So if you remember what a bromohydrin was, we added Br2, H2O, we added our Br and our OH Markovnikov and 100% trans. And that's what you're going to need to know for every single reaction that we've done for Friday. To be able to write the product, you need to know what am I adding, how am I adding it, Markovnikov, anti-Markovnikov, cis-trans, or 50-50. So that's what we know we'll add. So we end up adding the bromine and the OH trans. And that works out well for one of the things we can use bromohydrins for, which is making epoxides. Because what we're going to do is take the bromohydrin, I'm going to add a base that's going to go ahead and deprotonate the OH of the bromohydrin and make an alkoxide. Normally that alkoxide would act as a base, but now it's set up perfectly to react with this carbon and kick off the bromine and do an SN2 reaction. So even in a ring, because I added the Br and the OH trans, the alkoxide will be trans to the bromine to do backside attack. And when it does that, you end up with the epoxide. So this really only works because the bromohydrin is trans to begin with. So that's one way to make an epoxide. That's kind of a longer way. There are reagents that will make epoxides in one step. This is not that one. Okay, but it kind of builds on what we had learned before. The one-step method is to use what's called a peroxy acid. And a peroxy acid basically just is a carboxylic acid with an extra oxygen in it. That's all the per means. So like when we talk about hydrogen peroxide, well, water in essence is hydrogen oxide. So hydrogen peroxide just has an extra oxygen in it. Peroxy acid has an extra oxygen in it. That extra oxygen is going to end up adding to the double bond. Specifically, what you'll see if a reagent's listed is what's called MCPBA. And MCPBA is a very specific per carboxylic acid. There's two O's there. It's called metachloroperbenzoic acid. And that's a structure, you don't really need to know it, except that in sapling they don't talk about a peroxy acid, they talk about MCPBA. So when you see MCPBA on your sapling, that's what they're asking you to do, is to do this epoxidation reaction. Okay. And so what happens is that the oxygen of the peroxy acid is bonded simultaneously to the two carbons in the double bond to make the epoxide. So it kind of just sits on top, forms the two bonds simultaneously. That sets up a new type of stereochemistry, a new term. We have stereoselective, we have regioselective, both of which deal with the products. We talk about, for stereoselective, we're making products that are stereoisomers. Regioselective, we're making products that are structural isomers, and we choose one of those. Stereospecific, you'd think it means something else, but it doesn't. What stereospecific means is that if you change the stereochemistry of the reactant, you get a different product. So here's the first example of that. So if we have this trans alkene, what we'll end up forming is the trans epoxide. So because the oxygen comes in, sits on the double bond, forms the two bonds simultaneously, there's no rotation possible or anything like that. You form the trans alkene gives you the trans epoxide. Now in this case, the stereochemistry is what we would call preserved. Doesn't always have to be. What stereospecific means that if you change the stereochemistry, so if I took my epoxide, if I take my double bond and I now make it cis, and I use my peroxy acid on it, and I'm going to stretch that all the way over there, what I'm going to end up forming is, I'm going to end up forming the cis epoxide. So if I change the stereochemistry of the reactant from cis to trans or trans to cis, the stereochemistry of the product also changes. And that's what stereospecific means. Change the stereochemistry of the reactant, you get a different product. Different product stereochemistry. So in this case, it's retention. Cis alkene, cis epoxide. Trans alkene, trans epoxide. And that's what stereospecific means. We've seen a stereospecific reaction prior to this. We didn't call it stereospecific, but I will now. SN2. Right? If you change R to S, you get a different stereochemical product. So SN2 is stereospecific. But in that case, it's not retention of structure, it's inversion of configuration. So some stereospecific reactions cause inversion, some are retention. And so in that case, SN2 is stereospecific. And biochemistry and molecular biology is really, you'll hear the phrase, they talk about it being stereospecific, or stereospecificity is the key to biochemistry, the key to molecular biology, genetics, etc. Anything on the molecular level. That's because we do have a lot of enzymes and a lot of other biochemical processes that change if you change the stereochemistry of the reactant. So the reaction is stereospecific for one of the two enantiomers. Sugars are like that. In lab, we took sucrose and we did a fermentation on it to form ethyl alcohol. You didn't really need to use sucrose. You could have gotten away with glucose. So glucose and yeast will ferment glucose as well. Sucrose is just glucose and fructose together. But sucrose, if we had glucose of the D form, that's okay. Our enzymes can metabolize that. But if we have glucose of the L form, and I'm talking rotations now, there's more than one there's more than one stereocenter, more than one chiral center in each of those two sugars. But if we have the enantiomer of the D-glucose, L, our bodies can't metabolize it. So if all of a sudden all the chiral carbons change in glucose, we're dead. Because we can't metabolize glucose. And there's lots of reactions like that. You can think of some of the chiral drugs. There's I think L-Dopa that is a pain medication, and D-Dopa does nothing. So those are stereospecific reactions. It's just they're stereospecific reactions where you get one enantiomer reacts and the other one doesn't. I guess those are two different products. You get a product, you don't get a product. So that's the specificity that's involved. There's a popular essay question that people will give, like if Alice walked through the mirror to go into the wherever she goes. I think there's rabbits involved and stuff like that. And there's a hatter that's mad because he's using mercury to make hats, and mercury is a neurotoxin, so that's why he's mad. He's not mad angry, he's mad neurologically damaged mad. But if she goes into that world through the mirror plane, she'd have a tough time eating because all of the sugar on the other side would be the wrong kind. So sometimes people will ask that question, like, if she did that, what would she be able to eat? And what processes would be different? It's more of a biochemistry essay question than it is an organic one. But the idea is a lot of biochemical processes are specific. This is the first encounter we've had with stereospecific that we call stereospecific. So that's what that term means. Sometimes people think that it's like there has to be a name for 100 to 0 in stereoselectivity or regioselectivity. There isn't. You might even think maybe this term is it. It's not. It has a totally different meaning. So when we epoxidize cis alkenes, we get cis epoxides and vice versa. So that's how we can do it in one step. This is by far and away the easiest way to do this. Okay. So once we make the epoxide, then what can I do with it? What I do with it is I open it up. I open up the epoxide. So what I'm going to do is I'm going to add a nucleophile underneath to one carbon. The oxygen is going to swing over, so I'm going to add a nucleophile to one carbon and have an OH on the other. That's how epoxides open up. There's two ways to do this. One is called acid-catalyzed, and the other is called base-catalyzed. And I'm not going to get into base-catalyzed. The problem with base-catalyzed is it's not base-catalyzed. It's strong nucleophile ring opening. This I could easily call weak nucleophile ring opening. And it needs an acid for it to happen. So because of the triangle, the nucleophile is going to add trans to the OH. That hopefully we can get. So first step in the mechanism is if I add H plus to an epoxide, if I didn't give you the final product, hopefully you would say, I'm going to protonate the oxygen, because that's what you're going to do. So you protonate the oxygen to form this oxonium ion. But the oxygen really doesn't want the positive charge. It'd be better if carbon had the positive charge. So how about the oxygen distribute its charge, its positive charge, down to the two carbons that it's attached to, and doing that by having two partial bonds. It still might have a little bit of positive charge itself, but if it gives the positive charge to the carbons, they're happier. And so we get this triangular intermediate. Now, where have you seen that kind of triangular intermediate before? Mercuration is like that because the Hg plus is partially bonded to both carbons, and bromination. Mary?
How can it be an intermediate if they're partial bonds?
That's a good question. Because really the intermediate is this, but I'm kind of drawing it like that.
We're not seeing it.
You're not? Why not? Oh. This is really the intermediate. This is kind of what it looks like for figuring out the next step of the mechanism.
So that's our transition state.
No, not really. It's like the bromonium ion. I mean, it's like the bromonium ion. You have the partial bonds with the charges distributed. So it's not a transition state because it exists. So these kinds of, bromonium ions are intermediates, and we write them with partial bonds. So these are ones that we do, I guess, right, with partial bonds. They're the first ones we've really done that with. So that looks like a bromonium ion. That looks like a mercury ion. Great. So when these lectures come right after each other, not a week in between, the reason that I talk about acid-catalyzed is because I say, hey, there's a triangular intermediate with delta positive charges, and everybody goes, hey, that looks like the bromonium ion, or nobody says that. But there's the bromonium ion. It has the same characteristics as a bromonium ion. It has the same characteristics as a mercury ion that we talked about last week. So then one of the ways I can open up this epoxide is to add water to it. So add acid and water. So then my water is going to come in, and so which carbon is it going to add to? Is it going to add to carbon A or is it going to add to carbon B? Now either one it adds to, it's going to be underneath. And either one it adds to is going to technically give me the same product because I've got two OHs. But that's okay, I'll change that in a minute. Right? Because I can go from adding water to adding alcohol, and all of a sudden, now it's going to add to one or the other, and we're going to be able to see it. So, the question is, where does the water add? Carbon A, carbon B, or I heard 50-50? So what do we think? Either way, it's going to add trans. So, but which one's it going to add to? How many people say it'll add to carbon A only? Carbon B only? 50-50? Okay, great. 50-50. So let's change it. It's a little surprising. Everybody's 50-50. Oh, there's 4 methyl groups there. So now I got this molecule. So how many people say that now that I've changed it, that the water's going to add to A only? The B only? 50-50. And I see most people are like, I don't know. You do. So water is what kind of nucleophile? It's weak. So weak nucleophiles can only undergo what kinds of substitution reactions? SN1. What drives SN1 reactions? Formation of carbocations. So water is going to add to the carbon that is least sterically hindered? Most sterically hindered. Most substituted. Why is it going to add to the one that's most substituted? But I don't have a carbocation.
Yeah.
No, I never will. Because if I do have a carbocation, that means the OH has moved over and given me a complete p orbital to add 50-50 to. And the OH actually doesn't add, the two OHs, they end up 100% trans. Because this is a triangular intermediate, so they end up 100% trans. So I'm not going to form my carbocation. So where's the water? Why is it going to add where it adds, Michael?
I can't readily explain that, but I'm kind of confused as to how we're doing. Are we trying to do SN2 with a weak nucleophile?
Part of the characteristic of this will be SN2. In other words, it'll be backside attack. But the reason it's backside attack is because remember, normally we get backside attack because the p orbital in a carbocation we had 50-50. But with the triangle in place, there is no top lobe to add to, so it only adds underneath to the bottom lobe. So that's the SN2 backside attack characteristic, but this is a weak nucleophile, so where it adds is characteristic of SN1. Patrick?
Does it add to A because it's more substituted, it's more positive?
More positive, you mean more
Yeah.
delta positive?
More delta positive.
We agree with that?
Yeah.
So in other words, that has the greatest delta positive charge. And when you are a weak nucleophile, the rules are you must donate to the poorest electrophile. Well, that carbon A has the greatest delta positive charge because it can take on the greatest positive charge because it's got those three. Well, it looks like a tertiary carbocation. If this was truly a carbocation, that would be, in quotes, a tertiary carbocation, and carbon B would be, in quotes, like a primary carbocation. So when you protonate the epoxide, you can get a regioselectivity of the attack of the nucleophile. It will attack the carbon that is most substituted. Why? Because that's where the greatest delta positive charge is.
So why when you switch make it the two methyls and then the two H's, is it 100% trans, but the original was?
No, this was a typo. This was a typo.
Okay, so it's always supposed
Yeah, I don't know why when I typed that slide up that I put the OHs there, because that gives you the impression that it had cis and it didn't.
It's the substitute. That's what we know is
All right, so everybody kind of with me in terms of where the nucleophile adds to the carbon that's most substituted? Thanks to Patrick.
Yeah, they're looking.
Thanks, Patrick.
No.
Should be thanks, Dr. Nichols, for doing that last week.
Yeah, I didn't cite my sources, but.
You can be failed for that. We talked about this last week. We talked about the idea of, well, let's be honest, I talked about it. This is a one-way discussion at the moment. The idea that in a triangular intermediate, that's how we explain regioselectivity is based on the size of the delta positive charge. The only thing different about what we did last week and what we're doing today is I don't have an O, or I don't have a Br plus that's added. I have an OH plus. But outside of that, there's nothing different. So what we used with the triangle last week to talk about regioselectivity is exactly what I'm using here with the epoxide. And again, had these lectures have come closer together than 7 days, hopefully you would have gone, hey, I think I've seen that before. Because you have. So that's how we can explain the epoxide, the acid-catalyzed epoxide opening. Now there's a base catalyzed or a strong nucleophile catalyzed ring opening that goes exactly the opposite. Because when you have a strong nucleophiles will want to undergo SN2, and what's important in SN2? Sterics. So if it's a strong nucleophile, it'll attack B. If it's a weak nucleophile, it'll attack A.
100% trans either way.
You get 100% trans either way because it's a triangle. Okay. So the end result of acid-catalyzed ring opening or with H plus H2O on epoxide is you've now added two OHs trans. You've got two carbons, and you've got two OHs that are trans to each other. And you may say, does this look an awful lot like, how does this relate to double bond, Markovnikov? It's not Markovnikov. But how does it relate to, why did I say there are you added two OHs? Because what did this start out as? That started out as a double bond. So after a series of steps, I ended up adding two OHs, in essence, to a double bond. And that's why we call epoxides kind of the intermediate compounds, is because they're intermediates along the way. So if you want to add two OHs trans to a double bond, what you got to do is make the epoxide an acid-catalyzed ring open it with water and acid. And that'll give you the two OHs trans. Okay, it's just the number of reactions. Because that's where we're at now. Now that we know some single reactions, we want to string them together to start doing some useful transformations. And one of them is to put two OHs trans. That's called a vicinal vial. Right? Now there's other things I can do with I can make that epoxide. I could say, okay, let's start with that. That's not what I wanted. I wanted this. I wanted to form my epoxide, so I form my epoxide, and I could add H plus H2O to it. That's kind of boring. Let's add my next switch. My next switch would be HOH, which is water, can be substituted by HOR, an alcohol. So now I've got my acid and my alcohol. Now I will definitely know where the alcohol added because it's not going to form two OHs. It's going to form an OH and an OR. So what would the major product of that reaction be? So what are we going to get? You're going to end up adding an OH and an OR. In this case, an OCH3. So where do you want to put the OH? Which carbon, top or bottom? Bottom? And then you want to put the OCH3 attached to the top carbon? How are they going to go? Trans. So we can put bold and dashed. Nope. So that would be the major product of that reaction.
Does the alcohol have to maintain its stereochemistry? Does it have to maintain being on a dashed bond?
Does what?
The methyl group? have to maintain being on the dash bond?
Not necessarily.
So they could flip and we could get them.
Actually, I don't know. Did I write the right product there? I don't know that I did. So let's go through the mechanism. So let me write the H plus there. So I'm going to go ahead and protonate the epoxide. So if I protonate the epoxide, I'm going to have my plus charge. And we know that that's going to then transfer the positive charge. So I'm going to end up with partial bond to the oxygens, and my delta plus is there. But the OH is still on top. So now I'm going to take my methanol, and I'm going to react my methanol, and it's going to attack which carbon? The top carbon. So it's going to come in and add there. So it's going to add from underneath. So that means my methyl group is going to be pushed up, and then my OCH3H is going to be there, and then my OH now is going to be like that.
So this is okay.
And then I'm going to lose my H plus because this is acid catalyzed. And so that's going to give me then my OCH3 on the dashed, my methyl on the bold, and my OH on the bold.
So there has to be an inversion.
So I guess I must have written the wrong product. No, I didn't write the wrong product.
So the HOCH3 goes in the top carbon because it's more positive.
Yes, because there's more delta positive, because the top carbon looks like a tertiary carbocation, and the bottom one looks like a secondary. So the top one's more substituted. And then it acts underneath, and then the OH, which was on top, swings over. So the OH is above the ring, and then the OCH3H is below. You lose the H plus, and you end up with that. So when I did this mechanism, I ended up with this. When I just wrote the product out, I just randomly wrote that product. They look pretty similar though, don't they? What is their exact stereochemical relationship between those two circled molecules? The enantiomers, they diastereomers, meso, same. Enantiomers? We all agreed that they're enantiomers? Top carbon, opposite configuration, bottom carbon, opposite, so they're enantiomers. So which one's the major product then? Both?
This is stereo specific.
They're both trans.
It's what? What's stereo specific?
This reaction stereo specific.
We got two reactions here. We have two reactions. The first reaction with the peroxy acid would be stereospecific, I guess. Well, if you could make a trans six-membered ring, which you can't, you'd get a different product. So we'll call it stereospecific. But the second reaction really isn't specific as much as it looks regioselective and stereoselective to me. Opening the epoxide. Because the products that I'm making, if I added the CH3OH to the other carbon, I get two structural isomers, and then I would get two different stereoisomers. So it looks stereo and regio to me. So which one's the major product? The top circled or the bottom circled? It's a racemic mixture.
It's gonna be a shot in the dark, but is the bottom one more stable if you look at it in the chair configuration?
I don't know, they can ring flip.
Didn't hit anything in the dark.
It's 50-50. Why is it 50-50? Because I made a pair of enantiomers. When do I make pairs of enantiomers that aren't 50-50?
You react with a chiral reagent.
When I've got a chiral reagent. So in this case, see, the thing is, okay, this product right here came when the the bottom product came when the OH was above the plane of the ring. But what happened if the OH was below the plane of the ring and the methyl group was up? I would get this product. Does it matter? Well, no, it's the same thing. Because there's two enantiomers of these two. And having the ring up and the methyl group down, and having the ring up and the methyl group down, those two are enantiomers. So you get a 50-50 mixture of those two. So it didn't matter which product I wrote. But that's how we would write the mechanism. Then, okay, so how about I add HBr? How about an H plus and a Br minus to the epoxide? Sure, I could do that. I'd end up with a H on the OH and the Br on the other carbon. And I would form like the same product as I would get with the bromohydrin, except opposite regioselectivity.
So here, Markovnikov wouldn't.
Well, Markovnikov, it only in the sense of starting with the double bond. If I take the combination of the two reactions, then I could classify it as Markovnikov or Markovnikov from the alkene. It's the final product. But these reactions are not considered to be Markovnikov. That term just doesn't apply for the epoxides. Markovnikov, anti-Markovnikov only apply to adding to double bonds. But we'll go over that a little bit later.
So since we're adding two things.
Right. I mean, the net result is we're adding two things, and in this case, we're adding an OH and an OCH3. We can't do that with a straight double bond. We can't go from double bond directly to here. But if I was adding an OH and a BR, then I can do that. And so we need to compare and contrast. But we'll do that later. No sense in confusing the issue more than it already is. But. Okay, so those are just electrophilic additions. There are some non-electrophilic additions, meaning that there's no electrophile, no nucleophile. We're going to simultaneously add two groups to the double bond without there ever being a charge. And that's what these non-electrophilic additions are. First one's hydrogenation. So if you want to add hydrogen across a double bond to reduce a double bond into a single bond, and remember from lab that oxidation and reduction, well, apparently no. Oxidation means that you add oxygens or remove oxygens from a molecule. Reduction means you add hydrogens or Oxidation means gain oxygens, lose hydrogens. Reduction means gain hydrogens, lose oxygens. I'd say remember that from lab, but only half of you would remember that from lab, because I don't think Dr. Simmons went over that. So in organic chemistry, that's how we define oxidation. Gain of hydrogens or loss of oxygens in both directions. It's easier than trying to figure out electrons. So in this case, I'm reducing because my alkene is gaining hydrogens. So if you want to hydrogenate a molecule or hydrogenate an alkene, you use hydrogen gas, platinum, or palladium metal. And I'll show you the quote-unquote mechanism of this in a minute. I'll just show it to you so you can remember it's cis, but it is cis. There's no sense of talking about regioselectivity here because it's a symmetrical reagent. I'm adding 2 hydrogens. Can't be regioselective. Stereoselectivity could be because I'm adding 2 hydrogens. So it could be stereoselective. Hydrogenation, you've heard about hydrogenated stuff, right? Partially hydrogenated stuff is like kills you or whatever. Does bad things to your cholesterol. But what they're doing is they're taking a long chain, usually a fatty acid, and there's a double bond somewhere in the long carbon chain, and they're turning that double bond into a single bond. Molecules that have long chain fatty acids are typically, long chain fatty acids that are attached to a glycerol molecule are oils if they have a double bond. So like your coconut oil, your sesame seed oil, your whatever oil, vegetable oils all have a double bond in a long chain. When you reduce that double bond to a single bond, they become solids. So if you want to take a vegetable oil, hydrogenate it, you make Crisco. Probably slightly healthier than lard, but lard is all natural. There's no partially hydrogenated stuff in lard. So here's the mechanism. Hydrogen comes in, attaches to the surface of the palladium metal, then the double bond sits right on top of it. All 2 hydrogens add at the same time, so we can think about this making a square transition state like we did last week. So therefore the hydrogens have to add cis. That's just for you to remember that it's cis. I'm going to blow off carbenes for a minute. We'll come back to carbenes. You want to add OHs. We just saw how to add 2 OHs trans. Okay, it took 2 steps. Make the epoxide, open it up with acid and water. I can add 2 OHs cis 100% of the time by using cis hydroxylation. Again, reaction, if I'm going to add 2 OHs to a double bond, it cannot be regioselective because I'm adding the same thing. So it's a symmetrical reagent. But since I'm adding the 2 OHs cis, could be stereoselective. So cis hydroxylation is sort of the yang to epoxide hydrolysis where you get the 2 OHs trans. Now I can get the 2 OHs cis. How does that happen? 2 ways to do it. One is osmium tetroxide and peroxide. The other is KMNO4 and base. So base just means the pH is above 7. KMNO4 is the purple reagent you used in like Gen Chem lab for titrations. You can add it to aquariums because it like oxidizes all the loose organic crap and turns the aquarium nice and clear. KMNO4 is an oxidizer. It adds oxygen to stuff. The stuff that's floating around the aquarium gets hydroxyl groups on it and dissolves in water. It's as simple as that. And if it's a low concentration, not to kill the fish. But I'm going to add 2 OHs cis to the double bond. That's what I'm going to do. Now, here's a mechanism that you don't have to, again, memorize. But if you're saying, hey, why is it cis? Or how can I remember if it's cis? Well, here's how you can remember it's cis. Here's the actual electron flow from the double bond to the oxygen, pair of electrons into the manganese, and then double bond out to form the CO bond. So the manganese just picked up 2 electrons. It gained electrons. Gain electrons, let's see, it's Leo, the lion goes Gur. Gur is GER, gain electrons reduction. So the manganese got reduced and the other molecule got oxidized. Hey, it gained oxygens, that's what it got. But here's the critical part right here. We talked last week about having a 4-membered ring and not having enough space to add one group cis, or one group above and one group below, because 4-membered rings aren't long enough to stretch. 5-member rings aren't long enough to stretch either. So because both oxygens add with the manganese, it's a 5-membered ring, not long enough to stretch the 2 oxygens above and below. Same thing is true for the osmium. The osmium reacts to form that compound, and there's 2 O's here that are missing. The osmium is an incredibly expensive metal. So what happens is you use a small catalytic amount, and then in the final step, the peroxide strips off the osmium, leaves the 2 OHs behind, takes the osmium back up to osmium tetroxide, and then that, as a catalyst, continues the process. You just keep turning it over. So both of these are cis hydroxylations because they form 5-membered ring intermediates. And by intermediates, I do actually mean intermediate compounds. But we do isolate the final product. Okay? So, we have a couple of reactions left to finish up with alkenes that we'll do probably for Monday. And then Wednesday will be review for the test. So if you got questions, you should ask as soon as possible, but if not, bring them to class on Wednesday.